Hello and welcome to another lecture on time complexity. In this lecture, I am going to discuss big O of n. But before getting into this lecture, I highly recommend you to watch the introductory lecture on time complexity. The link is provided in the above and in the description. Let's dive into the lecture. Big O of n describes an algorithm whose running time grows linearly with the size of the input data. If the input size is n, the number of operations required to complete the algorithm is directly proportional to n. Let's jump into an example to grasp the intuition behind big O of n. This piece of code will go through a list of items to calculate the sum of all elements. At the beginning, we have a list initialization. Initializing the list with 6 elements is a constant time operation because the list is of fixed size. Therefore, this operation is big O of 1. Go to the following line where you call the function. Inside the function, we have a variable named total. The assignment of a value to total happens only once, regardless of the input list size. Therefore, this initialization step is a constant time operation. On the next line, we begin a for loop. This loop iterates over each element in the input list. If the list has n elements, the loop will run n times. This operation has linear time complexity, meaning the execution time grows proportionally to the input size. The same rule applies to the addition inside the loop. This addition operation is performed once for each iteration of the loop. Since the loop runs in times, this operation also contributes to the linear time complexity. And finally, the return statement executes once, regardless of the size of the input list. This operation is a constant time operation. Now, let's go through the list and perform an addition operation to calculate the sum of all elements. The for loop iterates over each element within the list, and each time, the total variable keeps a record of the previous state and updates itself according to the new element. Upon the completion of the loop, the total variable will contain the accumulated sum of all the elements. This depends on the number of elements in the list. Therefore, as the input size grows, the time it takes to execute also grows. After the loop has been completed, the function returns the accumulated value of the total, which is 21. As you can remember, we had different time complexities within our code. When combining these steps, we focus on the term with the highest growth rate as the input size increases. Therefore, in this example, the operation with a complexity of big O of n is the dominant term because it grows linearly with the size of the input list, while a constant time operation or big O of 1 remains constant and does not grow with the input size. Therefore, according to big notation rules, we drop the non-dominant terms. Now, let's consider another situation. Suppose we have separate but not nested loops. As you notice, the time complexity of each loop is big O of n. Therefore, having 2 big O of n results in a big O of 2n. According to big O notation rules, constant factors are not significant in big O notation. Therefore, big O of 2n simplifies to big O of n. Finally, if the input size is n, the number of operations required to complete the algorithm is directly proportional to n. This means that as the input size doubles, the time it takes to execute the algorithm also doubles, reflecting a one-to-one relationship between input size and the execution time. I hope you enjoyed learning, and thanks for watching this video. Please feel free to share your thoughts.